Okay, so we dealt with this equation here, x1, x2 times, okay, this is the Kohler Mugiano geometrical techniques for going from binary to ternary, estimating ternaries from binaries. And everything is based on this equation here. The gxs in the ternary is x1, x2 times alpha 1, 2, where gxs in the 1, 2 binary at point A equals x1, x2, alpha 1, 2, and so on. And the various methods are all based, as I say, upon this same equation. The only difference between the various methods is where we decide to put the points A, B, and C in the binary systems. So if you put A, B, and C at the ends of lines like that, then that's called the Kohler model, which then, so the gxs here is based entirely upon the values of this point, and this point. This is the Kohler tube model, this is the Mugiano model, dropping perpendiculars. That's the Mugiano tube model. These are two weird models, and there are actually 64 possible models. And as I said, for the tube model, there are actually 3. Here, even for this system, there are 3 too, because I've drawn this line parallel to this base, but I could have drawn it parallel to that side or that side. But these are the main ones. For the main ones, you would have the Kohler model, which is called symmetrical. You would have the Mugiano model, which is symmetrical. You have 3 possibilities for Kohler tube, which are asymmetrical because component 1 is different. And you have 3 Mugiano tube models because, again, you can choose this line to be any way you want. You can choose weird models if you wish. Sometimes we do, but rarely. Okay, now all these, I said if all these alpha functions back in this equation are, if all the alpha functions back in that equation are constant, then the binary systems are, if all these alphas are independent of composition in the binary system, then all the systems are regular, and then all the models, Kohler tube, whatever, are identical. Now this is based necessarily, and there's no way of getting around it, this is, they'll say this is simply purely geometrical and there's no assumptions, this is mathematics. No, it isn't. It's based on regular solution theory. Okay, what you're saying is, let's say the alphas are constant. If the alphas are constant, then alpha 1, 2 is n naught z n Avogadro over 2 times twice the epsilon of an AB bond minus epsilon of an AA bond minus epsilon BB bond, etc., etc. If alpha 1, 2 is constant independent of composition in the 1, 2 system, then that essentially means that the 1, 2 system, for some physical reason, obeys the regular solution theory, which means, to a first approximation, the most important thing in regular solution theory is the random mixing. You're assuming random mixing, and you're assuming the heat of mixing and the entropies are given by sort of the difference in the bond energies. Now I know this is approximate and so on, but this is the basic idea of a regular solution. You have a random mixing of components 1 and 2, and the alpha reflects the energy difference to form AB bonds. Okay, and now if we just keep this exact, so alpha 1, 3 is n naught z over 2 times twice the energy. I'm changing ABs for 1, 2s, I do that all the time. 1, 2, 1, 1, 2, 2. Okay, here we have 1, 3, epsilon 1, 1 minus epsilon 3, 3, and the alpha 2, 3 is the same sort of thing. We simply assume now, if we assume that these bond energies, so in the binary system we're assuming that the Z is independent of composition and that the epsilons are independent of composition. That's the assumption, the sort of physical assumption of the regular solution theory. If we assume now that these bond energies here in the binary system remain constant in the ternary system, so even though you go into the ternary system, the energy of a 1, 2 bond doesn't change. The energy of a 1, 3 bond doesn't change. So these epsilons still apply in the ternary system. Okay, and so then x1, x2 is then simply the probability in the ternary system now. If you have here's your atoms on the lattice, x1, x2 is the probability of finding a 1 and a 2 next to each other. Okay, so you've got x1, x2 times the energy of forming the 1, 2 bonds minus x2, x3 times. Okay, so this is just the regular solution theory applied into the ternary system. Okay. x1, x2 is the probability of the 1, 2 bond, whether you're in the binary or the ternary system. That's the probability of the 1, 2 bond if it's an ideal mixer, random mixture. Okay, so you just, if you plug this equation, this, and this into this equation, you have the regular solution for the ternary system in which you would have the same assumptions. If all these epsilons are independent of composition also in the ternary system, here we're assuming in the binary 1, 2 that epsilon 1, 2 is independent of composition in the binary. We're now saying that even if we add 3, the energy of the 1, 2 bond still stays constant, and so on. Then you get the regular solution theory. Okay. So if the binary systems are regular, then you would sort of expect the ternary system to be regular, but this equation is based on regular solution theory, in that what the assumptions are basically then that the energies of the bonds in the ternary system are the same as in the binary system. So the energy of a 1-2 bond is independent of the fact that you've started to add 3. Okay, so we have a 1-2 bond here in the 1-2 system. We have a 1-2 bond surrounded by 1s and 2s. If I start to add 3s, it doesn't affect the energy of this pair. Also, more importantly even, you're assuming that the system remains a more or less a random mixture in the ternary system, which is really your biggest assumption here. Okay, so if this works, in other words, if this is a good expression for going from the binaries to the ternaries, it's based upon the concept of regular solution theory. Now, we know that these alphas depend upon composition in the binary system, so alpha 1, 2 in the binary system varies with composition from along the edge from 1 to 2. So we express that as a polynomial. So along this 1, 2 edge here, alpha 1, 2 now is not constant, but it varies with composition. Okay, so we say that alpha 1, 2 then is, well, the different ways of doing it, let's do the let's do it as alpha 1, 2 then is Q 1, 2, 0, 0 plus Q 1, 2, X2, Q 1, 2, 0, 1, X2 to 1. For example, it's a subregular solution. So alpha 1, 2 now varies in this binary system, which means, as I said before, you're saying that the bond energies are maybe Z, or it varies a little bit in that binary system anyway for whatever reason. So now we can still use the geometrical model, but we say what value, so I said if the alpha 1, 2s are constant, then the alpha 1, 2 in the ternary is the same as the alpha 1, 2 in the binary. Okay, now we're saying, well, the alpha 1, 2s are not quite constant in the binary system. Okay, so we can still say the alpha 1, 2 in the ternary is equal to alpha 1, 2 in the binary, but at what point in the binary? And that's basically what this is. Here we're in the Kohler method, we're saying alpha 1, 2 at this point. In other words, this interaction term at this point is the same as at this point in the binary. Here we're saying it's the same as at this point in the binary, and here we're saying, okay, so it's just which point in the binary are you going to do it at? What is the logic behind these? Well, here the logic is that this is a line where the x2 over x1 plus, the ratio of 1 to 2 is constant along this line. This is the 1, 2 binary projected to the 3 corner. x2 over x1 is constant along that line, so the ratio of 1 to 2 is constant. Okay, so in the binary system 1, 2, this thing varies with the ratio of 1 to 2. Okay, well, we're saying in the ternary system it varies, this whatever ratio of 1 to 2 you had here, then it's independent of adding 3. That's what the logic is behind it. The Muggiano method. Why did Muggiano propose this? Well, this is simply the closest point. The logic is that this is a perpendicular, so the closest point geometrically to this point in the binary is that point. So, well, you're taking the binary composition that is closest to the ternary composition, and that sort of makes sense, I guess. Okay, so this is the point that's closest to that. But what I said I don't like about that, as I showed you yesterday, is when you get down to dilute solutions. If you had a system 1, 2, 3, and I'm trying to calculate, say, the 1, 2 interactions at that point. Now, yes, this point, or that would be the, okay, this would be the Kohler method, and this would be the Muggiano method. Now, yes, at that point, let's make this more flagrant. In the Kohler method, you're basing, this would be point A. So in the Kohler method, you're basing the alpha 1, 2 of this dilute solution on this point here, which is also a dilute solution. Here, with the Muggiano, you're basing the value here on a more concentrated solution. So this point may be slightly closer, but I think the Kohler is the more logical one. And this is borne out by some calculations. So I prefer I don't know, I prefer the Kohler model to the Muggiano. The Kohler tube model, you're saying now 1, 2, and 1, 3 are very similar. 2 and 3 are very similar materials, and 1 is very different. So say SiO2 with calcium oxide, magnesium oxide. We're saying that the alpha 1, 2 depends upon, this is the ratio along here, this line is X1 is constant, so this would be the ratio of 1 to 2, this is the ratio of 1 to 3, you would expect the alpha 1, 2 to be more or less constant, where you're replacing, I'm replacing 2, 2 is chemically very similar to 3. So as I move along this line, what I'm doing is I'm keeping the amount of 1 constant, and I'm keeping the 2, I'm just varying the 2-3 ratio. I'm replacing 2 by 3, which is very similar to it. Okay, so then you would expect it to remain constant along that line. And you can have a big difference between the symmetric and the asymmetric models, and I gave an example here. 2-3 was an ideal solution. 2-3 was an ideal solution, meaning 2 and 3 are very similar. And here we have GXS1-2 is very asymmetric, and GXS1-3 is also very asymmetric with exactly the same coefficient, so clearly you would expect as you moved across this line to have really no difference. Replacing 2 by 3 should keep the energy of the system the same. And that's what you get with the tube method. But if you use the Kohler method, then you're basing, as you move across here, you're basing the Gibbs energy and further up here, which varies tremendously, and you end up with something ridiculous like a two-phase region. So, okay, so that's where we were last time, but the important thing is that the regular solution theory is based upon the idea of random mixing and of the atoms and upon the bond energies being more or less expressed by a polynomial expression. And there's no way around it. And then you say, well, this is just mathematical, but okay, you could fit up, say you have a binary system where clearly it really isn't a regular solution. You're pretty sure it's a long way from regular. The excess Gibbs energy is very large and it's very asymmetric. You can still force fit something up to you can still force fit it to a polynomial expression. Okay, you're just fitting a binary system. If you're doing an optimization, you take a power series with 6 or 7 terms and you can get a pretty decent looking fit to the binary system. So you fit up all 3 binary systems, you force fit them using 6 or 7 parameters, and you make your binary systems, your optimization fits the binaries. Okay, but then, that's fine, but that has nothing to do with the physics. That's just you're taking a polynomial and you're putting in a whole bunch of terms and you fit the thing up. Then, however, when you use one of these methods to go from the binary to the ternary, now you're not just doing mathematics, you're doing chemistry. You are saying, you're making the assumption of random mixing and so on, and this is not true. Okay, so this is an approximation which is necessary. They talk about it being a mathematical approximation. Well, that's ridiculous. We're making a prediction of a physical property, so we must be basing it upon some physical model. Not a mathematical model, a physical model. The physical model. So even though you can fix up all 3 binary systems by force fitting them, if the physical model you use, to a mathematical model, if the physics behind it isn't right, the chemistry behind it isn't right, you're going to get a poor interpolation. So just because all the binaries are fitted up, it doesn't mean this is going to work. So when can you use the polynomial in Kohler tube Muggiano? Well, when you have some reason to believe the system isn't too far from a random mixture, and when the bond energies are more or less additive, or if you see that all 3 binaries are easily fitted to fairly small excess Gibbs energies with 2 or 3 terms, then okay, probably you can use something like this in the ternary system. But if they're not, then you can't do it, or you shouldn't do it. Also, the proof is that the different mathematical models can give you quite different results. If you try it with facts, say you use Kohler tube Muggiano, you can get different results in the ternary from exactly the same binary. So it is chemistry. All right, let's do a little mathematics now. Okay, so we're going to start with this equation. What equation? That equation. For the moment, we'll set all the ternary terms to be 0. Okay, by setting ternary terms to be 0, then we're assuming that the bond energies, or that the parameters for the binary system are all you need in the ternary. The ternary interactions are negligible. The binary interactions are enough to predict what goes on in the ternary. Can't get around that. So these alphas can be expressed as general polynomials. Q12ij is the notation we're using for the general polynomial. or you can rearrange these into a Redlich-Kister, where the IL12 are the Redlich-Kister terms. Okay, starting here then on page whatever. Suppose the data for the 3 binary subsystems have been optimized to give binary coefficients. So we've got all 3 binaries have been optimized. We now have these binary coefficients, Qi, J, Mn, or we have the Redlich-Kister parameters. And we want to then do GXS in the ternary system. Now you can do this, as I say, completely geometrically. Just point by point. We can take in the system here, say we're going to use this as 1, 2, 3. I have fitted up alpha 1, 2 has been fitted up to a polynomial, alpha 1, 3, and I want to calculate GXS at this point using, say, Kohler, so I draw 3 lines like this. I calculate the numerical values of the alpha functions at these 3 points, and I calculate it point by point. But what I would like is I would like an equation now that I can put into my software, so the software will do it. So basically, this is nothing different, this is just doing it for the software. I now have alpha 1, 2 has been fitted up to a polynomial, same with alpha 1, 3. I just want to get the computer to do this. I want to say use the Kohler method, these are my expressions for the alphas, and I want an expression, a mathematical expression for GXS. Okay, let me just write this out so I don't have to keep flipping back and forth. I have GXS then is alpha 1, 2 at point A times x1, x2 plus alpha 2, 3 at point B times x3 plus alpha 3. X1. Okay, so I'm going to use the Kohler method, which is this method like this. This line here, then let's take the line, this is the 1, 2, so this line here, going along this way, x1 over x1 plus x2 equals a constant along that line. Geometrically is equal to a constant, and x2 over x plus x2 is a constant along that line. Okay, so I want alpha 1, I want the alpha 1, 2 term along that line, so x1 and x2 along that line. So we have chosen to use a Kohler type approximation. Along that line, the ratio x2 is constant. Furthermore, this ratio is equal to x2 at this point here. Okay, this ratio is constant along this line. Let's say x2 is also x1, x2 is their constant, and at this point, x1 at this point, this is equal to x2, because on the binary system here, x1 plus x2 is equal to 1 in the binary. It's not equal to 1 in the ternary system. Okay, so at this point, x2, at that point, this ratio is equal to. Okay. Therefore, the function alpha 1, 2 can be written as follows. We want alpha 1, 2 to remain constant along this line. Right? I want alpha 1, 2 to remain constant along that line. Okay, x2 over x1 plus x2 is constant along that line. Okay, so if I write alpha 1, 2 is in the binary system, at this point in the binary system, alpha 1, 2, at that point in the binary system was the sum of qi2 whatever, times x1 to the I, x2 to the j. That's the value of alpha 1, 2 in the binary system. Okay, I want that alpha 1, 2 to remain constant along this line. Well, along this line, x1, x2 over x1 plus x2 is constant, x1 over x1 plus x2 is constant. So if I replace alpha 1, if I replace these values, okay, in other words, this function here is constant along that line. And it's equal to this value at that. See what I've done? Okay, so I just replace x1 and x2 in this equation by this ratio. So this function, along this line, this function, I may have made too much of this. Along this line, x2 of this function here and this function here are constant, so clearly along this line, this function alpha 1, 2 is constant. And at the end point here, this is equal to x1 and this is equal to x2. So at the end point, it's equal to the value of the binary and stays constant along that line. So that's all you do, you just replace. So you then take, if you want, so then in the computer, if you want to write the algorithm, you take this equation here, and you replace x1 and x2 by this and this, and you replace x2 and x3 clearly by x2 over x2 plus 3, x3 over x2 plus x3, and you end up with the Kohler mathematics. Or if you're using the Redlich-Kister expression, well, if you use the Redlich-Kister, so we have two things. We have the polynomial here with the q's, or we have the Redlich-Kister with x1 minus x2 along that line. So the Redlich-Kister, this function then will remain constant along that line because of x1 and x2. x1 minus x2 over x1 plus x2 is also constant along that line, of course. This function here is constant along that line. And at this point in the binary, where x1 plus x2 equals 1, it's equal to the binary coefficient, which is x1 minus x2. So this is just rearranged. Okay, so alpha 1, 2, this alpha 1, 2 is constant along that line and equal to the binary value at that point. Remember when you're reading this that x1 plus x2 equals 1 in the binary, but not at the turn. Alright, so if you're doing a Kohler method, you just replace these values. Now suppose you want to use a tube type approximation along, you're now using a tube type approximation along lines of constant x1. Okay, so now I want to base it on something that looks like this. So this is 1, 2, 3, and here I have alpha 1, 2, and I want it to be constant along the line of constant x1. So alpha 1, 2 should be constant along that line. So what do I place now? I'm going to take this x1, x2 here, and I'm going to replace it. I'm going to take alpha 1, 2 here. Sorry, what I said before was wrong. You do not replace. Let me go back. Back to the Kohler tube. It's alpha 1, 2, which is written by this expression. You do not replace the x1, x2. Alpha 1, 2, this expression is still used, and this is what you use for alpha 1, 2. You still keep the x1, x2 here. All right. Because x1, x2 is still the probability. This term is always there. This x1, x2 is the probability of a 1-2 pair based upon the ideal solution, ideal random mixing. This alpha 1, 2 is the energy for forming the 1-2 pair, and you're assuming that's constant along that line. If you now assume that alpha 1, 2 is constant along this line, then what do you write for alpha 1, 2 in the ternary expression? Let me write the binary. Alpha 1, 2 in the binary is equal to sigma q 1, 2 ij x1 to the I, x2 to the j. I think I may be confusing you a bit. Or alpha 1, 2 in the binary, if you use Redlich-Kister, is sigma 0 sigma I. Okay, those are the values in the binary if you're using from up here. If you're using the binary system, you would either have that expression for the binary, or you might have that expression for the binary. Okay, so the question is then, let me kind of start again. If you're going to use Kohler, then you want to replace these x1s and x2s, not these. You want to replace these x1s and x2s by something that's constant along this line. And that would be then x1 is replaced by this, x2 is replaced by this, and this is the expression you use for alpha 1, 2 in the ternary. Okay. Or if you're going to use the Redlich-Kister, x1 minus x2 is replaced by this ratio, which remains constant along that line of constant 2, 3 ratio. Now let's suppose, okay, let me go on. Now you want to use the tube approximation, and I want alpha 1, 2 to remain constant along this line where x1 equals constant. So this is a line where x1 equals constant, and I want alpha 1, 2 to be constant along that line. Okay, so I take the alpha 1, 2 binary expression, and I want to replace x1 and x2 here by something that remains constant along that line. Well, clearly along that line, x1 is constant, so x1 I don't have to replace it by anything, and x2 I replace it by 1 minus x1. Okay, so here's what I do. This expression then, this x1 times 1 minus x1 is clearly constant along that line, and it's equal to x1, x2 at that point. So for this expression, in the ternary system then, for alpha 1, 2, I write that expression, and that will be constant along that line. Or you do Redlich-Kister, it comes out this way. x1 minus x2 is replaced by 2x1 minus 1. This expression then is equal to the binary expression here, and it's constant along that line. And then if I'm using the the Kohler method, alpha 1, 2 then is constant along that line, so alpha 1, 2, you replace it by that expression. Similarly, alpha 1, 3 is constant along that same line, so alpha 1, 3 would be a very similar function, x1 times 1 minus x1. But for the alpha 2, 3, which is going to be constant along that line, you use the Kohler type expression. So the alpha 1, if you're going to use Kohler 2, the alpha 1, 2 and alpha 1, 3, you use this type of expression, and for the alpha 2, 3, you use this type of expression.
So alpha 1, 2 and alpha 1, 3 are equal?
No, alpha 1, 2 comes from fitting the binary data here, and alpha 1, 3 comes from fitting the binary data here. What I mean is if you're using this, then alpha 1, 3 in the binary is sigma q 1, 3 ij, and you replace x1 and x3 by. So, even though this is strictly mathematical, of course, now it's still geometrical. If you use this expression into here for alpha 1, 2, you're taking your mathematical terms for alpha 1, you're taking your expression for alpha 1, 2 here, but it's only the value at that point that's being used. It's exactly the same as if you evaluate the value of alpha 1, 2 at that binary point and make it constant here. So you're still basing it only on one point. In other words, all the other, you may have optimized this entire 1, 2, you're using data across the entire 1, 2 system from phase diagrams, whatever, to get your polynomial expression. So your coefficients here are based upon analyzing the entire composition. But when you're doing your Kohler tube interpolation, you're really basing it only on that one composition point here. It doesn't matter what it is here. Any expression for alpha 1, 2 in the binary that gave you, if you had two expressions for alpha 1, 2 in the binary which were the same at that composition, they would give you the same value in the ternary of this. So it's still geometrical. You're not adding anything by doing this, you're just putting it into your computer. It's still based upon one point. And the assumption is still random mixing. So. Okay, if we're going to use the Muggiano method, if we're using the Muggiano method, then we have a point here in the ternary, and it's going to be based upon this point in the binary, and along this line here. Okay, so this is a line going perpendicular from my ternary point to my binary point. And along that line, you can verify this at home, along a line going from a point B perpendicular to the 1, 2 side, these functions are constant. This function and this function are constant along that line. Play with that yourself, but I verify they are, and they're equal to x1 and x2 respectively in the binary system. So in that case, if you're going to use Muggiano, you replace x1 and x2 in the binary are replaced by these expressions, and then this expression then is constant along that line. Okay. Now, there's one other thing. If you use, now you have it along this line here, along this line, let's say along a line going from point B perpendicular to the 1, 2 side, x1 minus x2. is constant, okay, geometrically. So these things are also constant. Right? But now you see this makes it particularly simple if the 1-2 binary alpha function has been expressed as a Redlich-Gister polynomial. You don't have to replace it. X1 minus X2 is just written the same way. You know what I mean? So this is really simple now. You don't have to actually replace anything by anything if you use if the 1-2 binary system is fitted to a Redlich-Gister, then it already is in terms of X1 minus X2. So just keeping the binary term written out this way is constant along that line. But that is just a mathematical simplicity. I'll read this here. This is the reason, and there's no, I got Hillard to admit it. It was pointed out by Hillard. This equation can be substituted directly with no change. So that's what I just said. It's particularly simple mathematically. If you substitute x1 minus x2 into here, you don't have to change anything, so you just write out that expression that looks like, these look like binary terms. The Muggiano model then is called the Muggiano-Redlich-Gister model. But this is a misnomer. The use of the Muggiano model does not require that the binary alpha functions be expressed as Redlich-Gister polynomials. You can express, obviously, the binary functions this way, because that's just a rearrangement of that anyhow. There's no difference. This is the same as that. It's just different ways of arranging your terms. And then you write the thing out this way, and you got it. Okay, so it doesn't matter. Okay, so therefore, the use of the Muggiano model does not require that the binary alpha functions be expressed as Redlich-Gister polynomials. If alpha 1, 2 is expressed as a general polynomial, then you just do it this way, and they're still constant. Conversely, the use of the Kohler tube models does not preclude expressing the binary functions as Redlich-Gister polynomials. Okay, I can use Kohler and Kohler tube, and I can express these. I don't have to use, just because these are expressed by Redlich-Gister doesn't mean I have to use this Muggiano model. I can still use the Kohler tube. The two have nothing to do with each other. This just happens to be mathematically lucky, that if you happen to express these as x1 minus x2, it happens to be constant along that line. But this is no physical, this doesn't mean the Muggiano model is somehow physically more reasonable or something. Okay. And the Muggiano, Redlich-Gister, the only reason you use Redlich-Gister rather than the general polynomial in cases is because these coefficients tend to be a bit less correlated, as I explained. And they say, well, that it's a big mathematical convenience in your computer program. Well, not really. I mean, you can put this in your computer program, or you can put that in. I mean, what the hell is this? 2 more terms, okay? It's no simpler. Plus, although you can write out the excess term can be written out, and these look like the binary terms of the Redlich-Gister Muggiano thing. When you come to writing the expressions for the partial properties, they're not the sum of the binaries anymore. And they're no simpler, really, than if you use this. And you have to, in your computer program, write first and second derivatives of gxs, and that's no simpler. Okay, but this is the reason why people have, so Hillard and the group who ran the group in Stockholm have written the whole thing in terms of everything is expressed in Redlich-Gister, and then the ternary is expressed using the Muggiano. But this is really severely limiting in my mind. You don't have to do it that way, and there's no physical reason for doing it. So in the fact stage, we permit you to express the binaries any way you want. You don't even have to express all 3 binaries the same way. You could use Redlich-Gister here and a general regular polynomial here, whatever you want. And you can use Kohler tube or Muggiano as you wish.
Is it possible to separate by region, to use different kind of...
No, you have to pretty well have to stick to the whole. Okay, now let's just look at what I said by the weird method, though. Now you see that you're not really stuck to Kohler, tube, Muggiano, or whatever. It's really the alpha 1, 2. The alpha 1, 2 can be replaced by one sort of term, the alpha 2, 3 by another, and the alpha 3, 1. So I could do a weird model like this. I could take this value here, and I could take say a Kohler type thing down to here, a tube type thing over here, and a Muggiano type thing to here. And for my alpha 1, 2, I replace that by the tube type thing, x1 constant. For the alpha 1,3, I use a Muggiano type term, and for the alpha 2,3, I use a Kohler type expression, and I get it. So you can choose 64 possible ways. Okay, there are, and each ternary, okay, there are 64 possible ways actually in a ternary. I'm going from the binary to the ternary. All sorts of different ways you can do it. Okay. Whereas in the general SGTE and thermal calc, there's one way of doing it only. That's only the Muggiano model, which I think is far too limited. So you can do these any way you want in FACSI. Okay, because really the alpha 1,2, you're saying the alpha 1,2 function is constant along that line, so you replace the x1 and x2 by x1 and 1 minus x1. Alpha 2,3 is constant along that line, so you replace them by the ratios x2 over x2 plus x3, and the Muggiano is constant on that line, so x1 minus x2 stays constant along there, and then you x1 minus x3. Okay, so I might want to say one last thing, because this can be confusing. Way back a long time ago, okay, this is asymmetric. It's x1 minus x2, or to use x2 minus x1. Okay, because we started doing this back while the other people were doing it differently. We put x2 minus x1. And for historical reasons now, we still have a lot of our things are done in terms of x2 minus x1. In fact, Sage, you can do it either way you want. Okay, but it's just that a lot of our old fits were done in x2 minus x1. Whereas the general consensus among other groups is they use x1 minus x2. Okay, so you got to be careful. And you can use both. In fact, you just got to tell it which one you're doing, but I'd be careful because they're not always x1 minus x2. And then the even terms, if I is even 0, 2, 4, 6, it doesn't matter, but if it's odd, the terms just change sign. Okay, so the L12 terms here for odd values of I will be opposite signs depending on how you do it. But you got to be careful, we don't always follow that. Especially in some of the older fits we've done here, we use x2 minus x1. I think we try to use x1 minus x2 now simply to do what everybody else is doing. That was just a matter of convention, and we started it earlier than everybody else. Okay, so which model do you use? Well, as I said, if there's a big asymmetry, if one is different chemically from 2 and 3, I would certainly start with the Kohler 2 model and see what's happening. And you can try different. But sometimes, even if there is a difference here, we do have ternary data we find, and I mean, that a symmetric model might work better. So you can try them out. It's never completely clear what it is, and this is, of course, estimations, approximations. It's not a rigorous theory of any sort. But the more asymmetric these things are, the more and more if you had something where one is very different chemically from 2 and 3, I would hardly expect that anything other than that is going to work. If it does, then it's more like chance than good design. Okay, now how do we go? So we're doing a database. We're setting up a database and for a multi-component system. And so for each ternary system, we have chosen one of these techniques. Generally, if it's here, we probably will have chosen this one or this one. But this one, there's 3 possibilities here. So we have a bunch of systems, so we've chosen, for example, well, I think I showed it here, quite simple. I used, all right, let's say I have a 5-component system. And this is how the databases are built up. This is what this whole paper was about, actually. You have a 5-component solution. 1, 2, 3, 4, 5. And you have optimized all 5 binary systems. All right. And now you've estimated for each ternary system. And for each ternary system, you've chosen one of those models that I showed before. So for your 1, 2, 3 system, you've got a good fit using what this is my little cryptor, what do you call it? Notation, anyway. This means this is Kohler Muggiano. Okay, this means that this point is based upon these 2 points in this one. So I've used a Kohler Muggiano here. So 2 is the asymmetric component. 2 Muggiano. Right, 2 Muggiano. Here I have used this little cryptic little diagram, means I've used a Kohler tube, okay, along this way, with 1 as the asymmetric component, and based upon this. Is everybody clear to the? Okay, so for the 1, 2, 5 system, I've decided to use a Kohler technique. For 1, 3, 4, I've used a tube Muggiano with 1 as asymmetric. Here I've used straight Muggiano symmetric, and so on. And here I've used some weird methods. Okay, and so I have, those are all the ternary systems. And for some reason, whatever, I have 1, 2, 3, 4, 5, 7, 8, 9. There are 10 ternary systems in this 5-component system. And when I was doing them, I optimized the binaries, then I optimized the ternaries, and for the ternaries, I chose those methods. Okay, that's all I have, and now but I want to put all 5 components into one database, and I want to use that database in order to estimate properties in the 5-component system. How do I join them together? Okay. Now, of course, if you're using thermal calc and that, you have no problem because everything's Muggiano, so you just Muggianoize everything. But what do you do here? Okay, so in most cases, okay, let's say if all five components are symmetric, then you just use Kohler for all the binary systems and everything's okay. Generally, this is the way we did it before, like meaning before we wrote this paper. If you have a system 1, 2, 3, let's say component 1, we use Kohler or Kohler 2. Okay, either Kohler or Kohler 2. So here we're using Kohler 2 for 1, 2, 3, and we're saying that's because 1 is different from 2 and 3. Okay, so generally what we find, if we have several components, we found that in most cases, and this is the way you'll see FactSage database is written this way, this is important for the stuff you're doing, because you do this in most cases, we divided the components into group 1 and into group 2 in terms of their chemical terms. So in other words, if you had, say, if you had silica, let's say you had silica, germanium oxide, calcium oxide, magnesium oxide, and lead oxide. These are acids, these are bases. Okay, so you would put group 1 would be silica and germania, and group 2 would be calcium, magnesium, and lead oxide, which are the bases. So you divide things into group 1 and group 2. All right. Okay, so now if you have binaries, if you have a ternary system 1, 2, 3, in which all 3 members are the same group, then you use Kohler. If you have a ternary system 1, 2, 3, in which 1 is in group 1 and the 2 here are in group 2, then you use Kohler 2, or vice versa. If there's 2 up here and 1, you'd use. Okay, if there's one, there's either all 3 are the same, in which case you would use in the same group, in which case you use Kohler, or 1 is in one group and 2 are in the other group, in which case you use Kohler 2 and put the odd one up, the asymmetric one up here. And that is the way you generally do it. You end up with 2 groups and you can do things that way. And then it's really quite clear how you're going to, from there it's fairly clear how you go into the ternary system, how you go into the 4 and 5 component systems. But in general, we find that, well, you know, if you have, for example, I have a 4-component system with a group 1 up here, and here I have a group 2, I have a group 2, and I have a group 2. Well, then I was going to take a plane across the middle of this constant, cross along the plane. If this is group 1 and these 3 are group 2 at the base, then I would take a plane parallel to the base and the alpha ones. It's kind of like a tube method along. But if I want to do it generally, how do I do it? And it has to be completely self-consistent and make some sort of physical sense of how we put all these things together. And I'm not going to go through this, and you don't actually have to know all the mathematics because the computer does it for you, but you have to know when you get into FactSage. So I'd like you to read this by yourself, Extension to Multi-Component Systems. So there was an earlier publication which you can look up. We developed a general method for, so this is what I said here, if you have the Kohler method, we generally use either Kohler or Kohler 2. We then divided everything into a group 1 and a group 2, acids and bases or whatever. And in many, many cases, in most cases you can do this. So if you're dealing with with oxides and your slags, you can put all your basic your acid oxides up here, silica, germanium, phosphorus, and so on, and your basic oxides down here. It usually works. Except what do you do with alumina? Alumina can be amphoteric in the middle. And sometimes you want alumina, and we find in some ternary systems alumina fits best here to use a Kohler tube, and in other times it fits best here. And I don't think there's any real physical reason for this, but we find that if we take a particular system, silica, alumina, calcium, or whatever, the model you use, Kohler or tube, and which is the asymmetric, can vary a bit. And then we could no longer do this by dividing them simply into groups 1 and 2, because then we ended up with inconsistencies. So this was developed as how you do it. So this thing is then based on that example I gave at the end of the 5-component system with the 10 systems that I chose in random ways, and this shows you how to put them together. And this is not the sort of thing you can talk about in class because it's impossible to follow it, but if you want to read it, there you go, and you can probably see the logic behind it. And that is what ThermFact does. Okay, so if you choose, so when you're setting up your database in FactSage, you're permitted to you're permitted actually to specify whether something's in group 1, group 2, group 3. You can specify a group number. Okay, there's one way of doing it, and that would be in a multi-component system. For every ternary system, you specify how you wanted to do it. Kohler, tube, Mugiano, weird. There's 64 ways of doing every ternary system. So that's the best way of doing it. The problem then is, though, that if you have a 10-component system, which you do, you end up with something like, I don't know how many ternaries, 5,000 or 800 or 900 ternaries, and you have to specify every single ternary system. Okay, so in most cases you can divide things up into groups of compounds, often 2, sometimes maybe 3. We might have group 1, group 2, group 3 are the amphoteric oxides or something. Okay, and then you simply say you enter a component, then it says give the group number. So you give group number 1, 2, or 3, or whatever. That fixes the group number. Then automatically it sets it up. If all 3 are in the same group, it does Kohler. If all 3 are in different, if the one's in the group, one group and the 2, all 3 are in different groups, it uses Kohler. If 1 is in group 1 and these 2 are in the same group, then it uses a Kohler tube automatically. So that covers most cases. That would cover most symmetric and asymmetric systems. But if you want to make an exception, then down at the bottom of the database you have exceptions. And then you can override. So you put everything into a group, and then at the bottom you can overwrite and replace something if you want to replace it by. Okay, and that we find is the most efficient way of doing it. So if you look through the oxide database, you'll see there's groups 1, group 2, and group 3, I believe. And most of the systems are automatically assigned Kohler or Kohler tube, depending upon whether they're symmetric or asymmetric. But then at the bottom, there's a bunch of systems in which it's overwritten, in which you specify exactly how you want to do that ternary system. And then these general equations are used to put everything together. And that's what this paper was all about. So you might find the mathematics interesting here. Okay, let's take a break. Continue on.